Welcome to our mobile software presentation on do you have the energy for this meeting? An empirical study on the energy consumption of the Google Meet and Zoom Android apps. This is a joint work of a team from the Free University Amsterdam, Leonhard Wattenbach, Basel Aslan, Matteo Fiore, Henley Roberto Verdecchia, and Ivano Malavolta. Why is this research important? This study focuses exclusively on the energy consumed by videoconferencing apps on Android devices, namely Zoom and Google Meet. Our experiments measure the energy consumption of popular videoconferencing apps on Android. We study multiple scenarios to improve the generality of our results. We make an in-depth comparison of the energy consumption, allowing us to represent the real-world usage patterns of these apps. Our results document empirical evidence of which features are more energy greedy and how features can impact differently energy consumption across apps. And our study provides in-depth empirical insights into the energy consumption of mobile video conferencing apps. So the goal of this research is to analyze video conferencing applications for the purpose of evaluation with respect to their energy consumption from the point of view of users in the context of Android applications. And the ultimate goal is to empower users to make their device last longer, both during the usage of the apps and in preventing the battery from degrading in capacity. Our study considers the following main research question. To what extent does the energy consumption differ between video conferencing apps? So we compare the two most popular and free video conferencing apps from the Google Play Store, namely Zoom and Google Meet. We measure the energy consumed during a fixed-length video conference, executed under different settings, and detailed in the following subquestions. So first, what's the impact of different number of participants? With increasing number of participants, the incoming data stream is increased as the video and or audio of more participants has to be transmitted. Second, what's the impact of using the camera? Since the camera has to be powered on, the video streams has to be processed and transmitted to the server. Third, what the impact of using virtual backgrounds. So also virtual backgrounds require computing power to identify which portions of the video belong to the foreground and background. Fourth, what's the impact of using the microphone? So activating the microphone increases the transmitted data and hence the energy consumed.
In this section, we'll talk about the experiment design and the thinking process that we use for planning our data analysis. As subject for this research, we decided to choose the two most popular apps available on the Google Play Store. Their popularity was verified across multiple websites and publications over the last 2 years, and we ended up choosing Google Meet and Zoom. Talking about the experimental variables, for all the research questions that we have, there is only one dependent variable, which is the energy consumption and is measured in joules. And we were also able to define one independent variable for each of these research questions. These independent variables for research question 1.1 is the number of participants between 2 or 5. For research question 1.2 is the front-facing camera. For research question 1.3 is the virtual background. And for research question 1.4 is the microphone. To be able to answer our research question, we formulate the following null and corresponding alternative hypothesis, in which we look at the possibility for the application to have the same amount of energy consumption based on different number of participants, or the case in which the user is activating or not the camera, the virtual background, or the microphone. In this table is shown how the treatments are assigned to each of our subjects in order to answer our research question. This investigation uses a complete design since it allows testing all combination of independent variables hence reflecting the potential usage of the apps in the real world. In our investigation process, we decided to go through the sub-question first and then answer our main question, which is establishing the most energy efficient app between our two subjects by evaluating the result coming from these sub-questions. But before getting any values from our experiment execution, the research team already planned to split up the data analysis in 4 main phases. In the data exploration phase, we use some histograms and some plots to visualize the measured energy consumption of the two apps in order to gain a preliminary insight into data trends. Normality testing, we analyze the distribution of the measured energy consumption to detect whether a sample comes from a normal or non-normal distribution via QQ plots, the Shapiro-Wilk test, and frequency distribution plots. This analysis allows us to check whether parametric or non-parametric statistical tests can be utilized for our hypothesis testing. Hypothesis testing, a phase in which we answer the research question of our study by applying a statistical test. The team decided to choose a Dunn's test in case the data collected is normally distributed, or the Mann-Whittney non-parametric test in case the data collected is not normally distributed. Effect size estimation, we decided for Cohen's d in case of normality or Cliff's delta statistic in case of non-normality to assess the magnitude of the experimental effect of our independent variables on the measured energy consumption. We will now talk about the experiment execution, which involves a preliminary experiment and also the experiment setup. For the purpose of correctness and feasibility of our experiment, a pre-testing phase was performed. In this preliminary phase, the energy consumption of each application is compared for different video conference lengths in order to verify that the energy consumption grows linearly with the time. In this picture, we show the setup that we use for our experiment. On the same Wi-Fi network, we connected the computer and the Android device. We use a computer with high specs to run different instances of the video conferencing application, since we used this device to simulate the participants joining the conference. The computer is also used to control the smartphone. They are connected via USB and communicate with the Android debug bridge. The Android runner framework is used to run the experiment with a specific config file for every different treatment. Each treatment lasts for 3 minutes and is performed for 20 runs with 1 minute of cooldown between each run. Battery stats is utilized to estimate the amount of energy consumed in our experiment. To implement a fully automatic and replicable execution of our experiment, we use Monkey Runner to simulate the operation performed by the mobile user on the app.
Then the results of the experiment. I'll first present the results of the preliminary experiment and then of the actual experiment. The preliminary experiment was about whether it is representable to only look at video conferences of a quite short duration or not. For this, we performed calls of different durations between 3 and 10 minutes. And as you can see here, you can draw a perfectly straight line through the data points with the duration on the x-axis and the energy consumption on the y-axis, both with linear scales. Thus, the energy consumption grows linear with the duration, and we can simply use 3-minute video conferences for the following experiments, which makes it feasible to perform more repetitions. We started the data exploration of the experiment by comparing statistical characteristics of our two subjects, Google Meet and Zoom. In this table, you can see that both median and mean are slightly higher in Meet, averaged over all measurements with different treatments. We've also plotted the energy consumption of the two apps as a histogram, Meet on the left and Zoom on the right. It is remarkable that both figures have two peaks, one at around 300 joules and the other at around 900 joules. We'll now take a look at the different factors, and we'll start with the number of participants. In this violin plot, the energy consumption is on the y-axis. The two violins on the left are representing Meet, the two on the right Zoom. The red ones stand for the 2 participants, while the blue ones stand for 5 participants. You can see that there is not a large difference between the two respectively. For Meet, more participants slightly increase the energy consumption, while for Zoom it even decreases a bit with more people. Again, we have this distribution with the 2 peaks. For camera off versus on, we get a very different violin plot. Red is camera off and blue is camera on. You can see clearly that the energy consumption is for both apps a lot higher when activating the camera, by a factor of about 3 to 4 times. On the other hand, it is the lowest measured energy consumption in a run with the camera on. But since it is only that single run, it can be assumed that this is an outlier that is influenced by external factors. If we cut off this outlier and zoom in a bit, we see that 3 of the 4 violins again have a distribution with 2 peaks, but in a much smaller extent this time. The next factor is the virtual background that you can activate to cover what's behind you in a video conference. Of course, a virtual background only makes sense when the camera is on. Therefore, we are only considering these ones here where the camera is on. Again, red means virtual background off, while blue means on. This figure is zoomed in, again because of the outlier. You can see here that the energy consumption increases, but way less than when exploring the influence of the camera. The mean grows here for both apps with a few percents. And finally, the microphone. As you can see here, there's hardly any difference visible between the two violins respectively. As mentioned earlier, we then first tested for normality to determine which methods to use for testing our hypotheses and for estimating the effect size. To test for normality, we plotted QQ plots for all distributions. Except for one exception, our distributions appear to be non-normal, which was also confirmed by the Shapiro-Wilk test. Therefore, we will use non-normal versions for hypothesis testing and effect size estimation. The Mann-Whittney test is such a test for hypothesis testing that doesn't expect a normal distribution. Additionally, we corrected our p-values via the Benjamini-Hochberg correction. Except for the microphone hypothesis for meat, all null hypotheses are confidently rejected. This means that we could observe a statistically significant difference between the two apps, as well as between the different configuration within both apps. As the last step of our data analysis, we performed an effect size estimation. To estimate the effect size, we used Cliff's delta, which returns a value between -1 and 1. These values can be then mapped to the 4 different effect size categories: negligible, small, medium, and large, according to these thresholds. We found large effects for both apps for the camera and for meat for the number of participants. Between the two apps, we found a medium-size effect. After having analyzed the data, we can now answer our research questions. Research question 1 asked whether there is a difference between the two apps in energy consumption. And we indeed saw a statistically significant difference with a medium-sized effect that consumes less energy. However, as the mean is only 4% lower, other factors such as usability or restrictions of the free version of Zoom should also be taken into account. Then the different factors. RQ 1.1 was about the number of participants. We could detect a statistically significant difference. It is remarkable that the energy consumption increases for meat, while for Zoom it decreases with more participants. Possibly this is due to the fact that Zoom exclusively shows the speaking person by default, while Meet displays all participants as a grid. RQ 1.2 was about the effects of the camera. This factor had by far the highest impact, with an increase of up to 285%. Thus, when the camera is not required, the most effective way to save energy is to turn it off. RQ 1.3 was about virtual backgrounds. Here we also saw an increase when activating, but with 2 to 3% much smaller. We actually expected a higher increase due to the extra computational work, but probably this is mitigated by a reduction of the video stream size. And finally, RQ 1.4, the microphone. Here we couldn't even see a statistically significant difference for Meet, possibly because the microphone might be deactivated when nobody is speaking. For Zoom, we could at least observe an increase by 2%, which is still quite small compared to the camera.
The validity of the experiment has been analyzed based on 4 classification types. So namely internal, external, construct, and conclusion validity, as proposed by Campbell and Cook. Internal validity, only the functionalities required for the experiment were running on the mobile device. For external validity, we selected and used a popular mobile device, so namely the Google Pixel 3. For construct validity, our measurements relied on energy estimations rather than direct energy measurements. Finally, conclusion validity, we ensured to systematically collect the required volume of data and conducted statistical analysis to draw conclusions. We also tested the normal distributions of our collected sample.
In conclusion, we were able to compare the most popular apps for Android, but also we were able to investigate how the hardware can drastically impact the energy consumption for this application. As a future work, we would like to replicate this test, trying to mitigating the threats to validity and also investigating how these two applications perform over 4G and 5G network. Thanks for your attention.